High-level synthesis, sometimes referred to as a C synthesis, electronic system-level synthesis, algorithmic synthesis, or behavioral synthesis, is an automated design process that interprets an algorithmic description of a desired behavior and creates digital hardware that implements that behavior. Synthesis begins with a high-level specification of the problem, where behavior is generally decoupled from, e.g., clock-level timing. Early HLS explored a variety of input specification languages, although recent research and commercial applications generally accept synthesizable subsets of ANSI C, C++, System C, MATLAB. The code is analyzed, architecturally constrained, and scheduled to create a register transfer-level hardware description language, which is then in turn commonly synthesized to the gate level by the use of a logic synthesis tool. The goal of HLS is to let hardware designers efficiently build and verify hardware, by giving them better control over optimization of their design architecture, and through the nature of allowing the designer to describe the design at a higher level of abstraction while the tool does the RTL implementation. Verification of the RTL is an important part of the process. Hardware design can be created at a variety of levels of abstraction. The commonly used levels of abstraction are gate level, a register transfer level, and algorithmic level. While logic synthesis uses an RTL description of the design, high-level synthesis works at a higher level of abstraction, starting with an algorithmic description in a high-level language such as System C and ANSI C, C++. The designer typically develops the module functionality and the interconnect protocol. The high-level synthesis tools handle the microarchitecture and transform untimed or partially timed functional code into fully timed RTL implementations, automatically creating cycle-by-cycle detail for hardware implementation. The implementations are then used directly in a conventional logic synthesis flow to create a gate-level implementation. History. Early academic work extracted scheduling, allocation, and binding as the basic steps for high-level synthesis. Scheduling partitions the algorithm in control steps that are used to define the states in the FSM. Each control step contains one small section of the algorithm that can be performed in a single clock cycle in the hardware. Allocation and binding maps the instructions and variables to the hardware components, multiplexes, registers, and wires of the data path. First-generation behavioral synthesis was introduced by Synopsys in 1994 as behavioral compiler and used Verilog or VHDL as input languages. The abstraction level used was partially timed processes. Tools based on behavioral Verilog or VHDL were not widely adopted in part because neither languages nor the partially timed abstraction were well suited to modeling behavior at a high level. 10 years later, in early 2004, Synopsys end-of-life behavioral compiler. In 2004, there emerged a number of next-generation commercial high-level synthesis products which provided synthesis of circuits specified at C level to a register transfer level specification. Synthesizing from the popular C language offered a crude abstraction, expressive power and coding flexibility while tying with existing flows and legacy models. This language shift, combined with other technical advances, was a key enabler for successful industrial usage. High-level synthesis tools are used for complex ASIC and FPGA design. High-level synthesis was primarily adopted in Japan and Europe in the early years. As of late 2008, there was an emerging adoption in the United States. Source input. The most common source inputs for high-level synthesis are based on standard languages such as ANSI C, C++, System C, and MATLAB. High-level synthesis typically also includes a bit-accurate executable specification as input, since to derive an efficient hardware implementation, additional information is needed on what is an acceptable mean square error or bit error rate, etc. For example, if the designer starts with a FIR filter written using the double floating type, the refinement requires additional information on the level of quantization noise that can be tolerated, the valid input ranges, etc. This bit-accurate specification makes the high-level synthesis source specification functionally complete. Normally the tools infer from the high-level code a finite-state machine and a data path that implement arithmetic operations process stages. The high-level synthesis process consists of a number of activities. Various high-level synthesis tools perform these activities in different orders using different algorithms. Some high-level synthesis tools combine some of these activities or perform them iteratively to converge on the desired solution. Lexical processing, algorithm optimization, control, data flow analysis, library processing, resource allocation, scheduling, functional unit binding, register binding, output processing, input rebundling, functionality, architectural constraints. Synthesis constraints for the architecture can automatically be applied based on the design analysis. These constraints can be broken into hierarchy, interface, memory, loop, low-level timing constraints, iteration. Interface synthesis. Interface synthesis refers to the ability to accept pure C++ description as its input, then use automated interface synthesis technology to control the timing in communications protocol on the design interface. This enables interface analysis and exploration of a full range of hardware interface options such as streaming, single or dual port RAM plus various handshaking mechanisms. With interface synthesis, the designer does not embed interface protocols in the source description. Examples might be direct connection, one-line, two-line handshake, FIFO, vendors, Bamboo from Politecnico di Milano with free source code at Panda Framework website, BlueSpec compiler from BlueSpec, Inc., MATLAB HDL coder from MathWorks, HLSQSP from Circuit Sutra Technologies, C to Silicon from Cadence Design Systems, concurrent acceleration from Concurrent EDA, Symphony C compiler from Synopsys, QuickPlay from PLDA, PowerOpt from ChipVision, synthesizer from Forte Design Systems, acquired by Cadence Design Systems on 2014, February 14. Catapult C from Calypto Design Systems, CyberWorkbench from NEC, C to Verilog from c-to-verilog.com, C2R from Sebitech, co-developer from Impulse Accelerated Technologies, Excite from Y Explorations, GAUT from Université de Bretagne Sud, Lab STICC, Hercules commercialized and marketed by Ajax compilers, LegUp from University of Toronto, Pico from Symfora, acquired by Synopsys in June 2010, Shang, Xilinx Vivado, XPilot from University of California, Los Angeles, VSYN from NG Design from Simflow, AUGH from Tima Laboratory, ROCCC, Panda from Politecnico di Milano,